Okay, so in this module, we'll be discussing part two of heat transfer. So we'll just delve into the calculations part of the more advanced um, things concerning conduction, convection, mostly. So ever since our discussion on mass balance, we've often assumed steady state condition in making our problems easier, although less likely to reflect real life situations. So again, when we say steady state, time has no influence on the temperature distribution within an object, although within that same object, the temperature may differ depending on the location. So kung isipin natin itong steady state, for example, if you're gonna take the inside of the refrigerator, you're going to assume in reality that any given point inside the refrigerator would say have a temperature of 7 degrees Celsius within the 24-hour period instead of fluctuating na sa umaga nagiging 5 degrees siya, sa tanghali nagiging 9 degrees. So, yun yung meaning ng steady state. On the other hand, if temperature changes both with location and time, then this is what we call the unsteady state. So although the steady state is an ideal condition, in our case, it would make calculation easier. Of course, when we have unsteady state, typically medyo maderivative na yung calculation nito and you won't be delving with that because our goal is to have an understanding of the concepts, and steady state makes that easier for us. So here is an example of steady state condition. Assume that this is the wall of a walk-in refrigerator or walk-in chiller. Within different points doon sa wall mo, as you can see, ay nagva-vary yung temperature ng molecules at that exact point within the thickness of the wall. However, kung steady state siya, through time, hindi nagbabago yan. Yung 18, 18 pa rin, yung 12 dyan, 12 pa rin, and so on. On the other hand, steady state may deal with having different temperatures at different locations in the room. No? So for example, halimbawa, dito sa point A, ang measure mong temperature ay negative 19. Dito sa point B ay negative 20. And sa point C ay negative 18.5. So steady state pa rin yun as long as the temperature at points A, B, and C respectively are the same. By the way, this is a data logger. It's used to record the temperature at the location at which it's placed. No? So we use this in the industry before, let's say, to monitor the temperature of the truck. The refrigerated truck as it travels from point A to point B para malaman kung may fluctuations ba and how it would affect our product's quality given that we worked with highly temperature sensitive ice cream products. So recall our equation on conduction through a rectangular slab from Fourier's law of conduction. The rate of heat transfer Q is equal to the thermal conductivity multiplied by the conduction area, the difference in temperature between the 2 points, and the thickness or the difference between the one point to the other. No? So yan, pag in-expand natin siya, the delta T and the delta X would be T2 minus T1 and X2 minus X1 respectively. And if we were to manipulate this equation to bring out one of the temperatures, okay, we could equate the other temperature to T1 minus the product of these, or rather this equation. Okay, and then we can see here we can do this to find out the temperature at any point x, no? So tulad na nakita nyo kanina, it will be a gradient from from x1 to x2. Any point within this thickness will have a linearly increasing or decreasing temperature based dun sa T1, T2, x1, x2. No? So you can actually find out the temperature from any point within this slab using this equation. So in this case, we treat the slab thickness as a similar to a thermal resistance circuit. Okay, and we can use the um, principles in circuit sa electricity para gawan ng equations ito. So recall from your physics or lessons about electricity, current is equal to voltage over resistance. If we were to consider the heat flow to be analogous to current and the voltage to be analogous to the temperature gradient, remember voltage is a potential gradient, we could rearrange our previous equation into this, okay, such that the denominator part could now be made analogous to your resistance. Okay? So, bakit ba natin kailangan gawin to? Perfectly fine naman yung previous version ng equation natin to tackle the problems we've been seeing so far. Well, the thermal resistance concept will be much easier to use if we're dealing with multi-layered walls. Now, for example, in a insulated refrigerator ninyo, hindi lang yan isang klase ng material, no? Meron kang yung parang bakal or plastic or a combination thereof sa outer portion, meron kang insulating material, and then meron kang yun pang pinaka plastic or bakal din niya sa loob. So, how would you look at the conduction through a layer of two or more different materials, each having a different um, thermal conductivity value, di ba? So, and a different thickness. So, when we are able to isolate the thermal resistance, kasi iisa lang naman yung heat flow doon, no? Yung Q mo, iisa lang across the many layers, but individually, there would have individual thicknesses and individual thermal conductivity values. So later on, we'll look at that, how to use this thermal resistance concept in multi-layered walls. All right, so in this case, we have one face of a stainless steel plate, 1 centimeter thick, maintained at 110 degrees C, and the other side at 90. Assuming steady state conditions, meaning it's all the side at 110 is always at 110, and the side at 90 is always at 90. Calculate the heat transfer per unit area through the plate, and also determine the temperature basically halfway into the plate o sa gitna ng plate crosswise. Okay, so the rate of heat transfer per unit area is Qx over A. So you put A over to the denominator and assign it a value of 1 meter. All right, so we have our T1s and T2s. You have your K value, and you have your X, which is basically for reference 0 and 1 centimeter yung excess mo, no? So if you plug in the values here, you'd get a Q over A of 34,000 watts per square meter, and you plug in that value here, tapos yung X papalitan mo ngayon ng 0.5 to get the temperature 0.5 cm or halfway through the thickness of the plate. Since this is linear, even without doing this calculation, you would probably interpolate that the temperature is also halfway between this interval. Therefore, 100 degrees C makukuha mong sagot dito, no? Now, suppose you have a tubular pipe heat exchanger, no? So may concentric pipes dito. Okay, the inner tube, meron siyang radius and therefore diameter, area. So when we're using Fourier's law, the equation now becomes the heat transfer rate equals to the negative of your thermal conductivity, the heat transfer area, and the difference in temperature and the difference in radii between the inner and outer. So meron kang radius inner, and radius outer, and that pinaka difference nila is the thickness that you will be using. Okay, so we will not go into the derivation of this equation, but that finally works out to be 2 pi L, or the length, kasi yung area is given by the length multiplied by the um, circumference of your circle. Okay. However, to get that value, we use the term ln, radius outer over radius inner. Okay. And similarly, the thermal resistance would then be equal to ln of the Rho over Ri over 2 pi Lk. Okay, let's look at the sample problem. There's a 2 cm thick steel pipe with 6 cm inside diameter conveying steam over a distance of 40 meters. So the pipe itself is 40 meters in length. Okay, the inside carries steam and the outside is open to the atmosphere. And if you measure the temperature inside and outside the pipe respectively, you would get 115 and 90 degrees Celsius. Calculate the total heat loss assuming steady state conditions. So first thing we need to do is to make sure that we get our givens right. Note that 6 cm is diameter and not radius. And thickness, if you're gonna add this to the diameter, idodoble nyo siya, di ba? Kasi taas tsaka baba yun ng paikot. Right? So therefore, the outside diameter is thus 10 cm, and therefore the outside radius is thus 5 centimeters. So RO is 0.05 meters and RI is 0.03 meters. Alright, so yun yung givens ninyo. And we just use that dito sa equation. You have your thermal conductivity K. So it's much higher because it's a metal. Okay. And then after plugging this, you get a value of around 529 kilowatts. So that's a lot of heat. Yun yung case kapag walang insulation, and that is why normally pipes that carry steam, especially over long distances, are insulated. Okay? Para mabawasan yung heat loss na yon, dahil yung, imagine that's 530,000 joules of heat per second. How much water could you have heated, or food you could have heated, if you minimize that loss value? So as we have mentioned before, in reality, itong mga walls or concentric pipes na ito contain more than one layer. No, kung parang sa bahay, lalo na yung mga bahay na gawa sa isang bansa, hindi lang yan hollow blocks, lalo na yung mga bahay na may winter, they usually have insulation. As I mentioned before, even yung refrigerator, if you cut away yung cross-sectional area, you know that there's an inner layer, an outer layer, and one or more insulation or functional layers in between. Similarly, ganun din sa pipes, no? As you've seen with the previous problem, you want to minimize the heat loss, and that's why you usually have one or two more layers to prevent, well, either heat loss or heat gain. Kasi kung malamig naman yung pipe mo, you'd also want to prevent heat gain from the surroundings. So, lalagyan mo rin siya ng insulation of some sort. And as you can see in this example, the temperature gradient would really vary from the inside to the outside. And kung makikita niyo yung parang temperature profiles niya, the steeper the temperature profile, the more insulating that material is. No? So kung makikita niyo dito, walang insulation because it's the same material. Halos flat siya. Then ito, material na slightly insulating, may konting slope siya doon. But this one really takes the cake, very steep. So it changes from 11 to 65 degrees in a small amount of time, in a small distance. So You can see the higher the difference between the 2 points of that material's walls, the greater the insulating capacity. So if you were to recall our thermal resistance concept and Fourier's law, so if we have a multi-layer wall, so halimbawa ito yung wall ng ref nyo, may tatlong layer dyan, each of a different material with a different thermal conductivity value. Therefore, though you would have an overall temperature gradient from point 1 to point 2, there are individual temperature gradients dun sa intersection ng kada material mo. And if you were to use the thermal resistance concept, we could look at these, no? So, again, yung heat flow through the whole thing, iisa lang, no? Kasi, syempre, kung ano yung amount ng heat na nag-flow through material 1, the same amount of heat must flow through material 2 and through material 3. So, that's the same throughout all calculations, but what would vary would be yung delta T na ginagamit natin would now be localized to the temperature gradients between dito, and also the delta X, or the change in thickness, would now be equal to the actual thicknesses of each material. Okay? And of course, you would be using the thermal conductivity value for each set, no? Then at the same time, we of course usually assume that the area is constant kasi rectangular slabs naman yan, no? So that's the same area here, here, and here. So in the previous slide, we saw that each of these terms was equal to their own delta T for the material, and therefore when you add the 3 delta T's, you can get the delta T for the whole series of materials, no? And if we arrange this equation para ilabas yung Q, which is the same value naman throughout, so ilabas mo yung Q and then i-transfer mo sa denominator etong natitirang terms, you now have an equation equal to dun sa kanina nating pinarallel na current is equal to voltage over resistance, no? Yung delta T mo, yung Q, tsaka yung thermal resistances. And therefore, these resistors in series, so to speak, additive yung thermal resistances nila, such that you can compute the individual thermal resistances, no, in the problem to make your problem solving much easier. Okay. All right. So let's look at the problem having multiple layered walls. No. So for example, Monvic hypothetically wants to lower consumption of the PFP by lowering the walk-in chiller's heat transfer to a target of 300 watts. If, for example, the total conduction area of the chiller wall is 3 by 5 meters, and the chiller wall is currently constructed from 10 centimeters thick concrete with a certain thermal conductivity. Given a thermal conductivity of 0.04 watts per meter degree Celsius, compute the required thickness of the insulation if the outer surface temperature is assumed to be 35 degrees and the inner surface is maintained at 5 degrees Celsius. So these are the following equations that you might want to use. Bear in mind that thermal resistance is equal to delta X of that segment over the Ka of that segment. So dahil yun yung mga given mo, we first find the thermal resistance of concrete, no? Equating Q to 300 watts, right? Here, so for example, if this is concrete halimbawa, so this is 300 watts, you have the thickness of 10 cm or 0.1 meters, you have the K value, and you have the area of 3 by 5 meters. So you can get the thermal resistance of concrete. Then you can plug it here, no? Since dalawa lang yung layers mo. And you know the delta T and the Q. You can use that to find out the thermal resistance of your insulator. And if you, once you get the thermal resistance of your insulator, pwede mo na siyang i-backsolve kasi ang kulang mo lang naman is yung thickness ng insulator, di ba? So equate the thermal resistance of the insulator to um, delta x over Ka, and then you can back solve that one. Okay, which would work out to be 5.7 cm. So to notice the impact of insulating materials in lowering the energy cost through lessening the rate of heat transfer, subukan naman nating tingnan kung ano ang mangyayari kapag purong concrete yung ginamit natin para ma-achieve yung required insulation mo na 300 watts. So since you only have one component, you can use the simpler form of the equation. So the thickness would be this one, no, in delta x mo. Alright, and you just transfer these to one side. Then T2 minus T1 over multiplied by Ka over your Gx. And you can get the the thickness value, which would be around 2.45 meters. So imagine kumuha ka ng basketball player, pahigain mo siya, ganun kakapal yung dingding ng konkreto na kailangan mo to achieve the same amount of material, the same amount of insulation as compared to yung 5.7 cm of insulation, which is just about this thick. Okay. So just like yung walls in series, we could also have composite cylindrical tubes in series, as is the case when, for example, dun sa steam pipe problem earlier, we added a layer of insulation on top of the steel to prevent the heat loss to the surroundings. Okay, so similar din naman siya, no? So we also use the thermal resistance concept. Okay. And although in this case, the thermal resistance would be equated to ln radius 2 over radius 1, 2 pi lka, ln radius 3 over radius 2, 2 pi lkb. So, assuming, of course, na may mga radii ka dyan. So, you just have to be careful kung anong set ng mga radii or radiuses yung gagamitin mo, and that you are using the radius and you account for the thickness as being added directly to the radius, no? As with the case kanina. Okay, let's try this sample problem. Let's say you have a stainless steel pipe with a certain thermal conductivity and the inside temperature is 130 degrees C. So most likely containing, let's say, superheated steam. If the pipe is 2 centimeters thick and the inside diameter is 8 centimeters, and also there is an insulation of 0.04 meters or 4 cm with a certain thermal conductivity, and given that the outside temperature is 25 Celsius, calculate the temperature of the interface between steel and insulation, assuming steady state conditions. Okay, so in the absence of specified length, we could assume a unit pipe length of 1 meter to make all our calculations easier by having one less multiplier. Of course, in this case, the results would be in watts per meter length, but of course, kung 1 meter naman yung pipe, then watts na lang yon. Alright, quick thing to take note of here again is kapag sinabi mong diameter, ito yon. So you have that for the radius. However, when you say thicknesses, ito yon. So you add those directly to the radiuses, no? So the way we go about it is we solve for Q using this equation. You have the 130 degrees Celsius minus 25 degrees Celsius here. T1 is the inner, mas mainit yung inner. Radius 2, radius 1, and radius 3, radius 2, which works out to be tawag dito, 4, 6, and 10 centimeters respectively. Okay, and then you have the A values, you assume an L of 1. You have the K values and you assume an L of 1. So you can get this, and it will be 45 watts per meter length of pipe. That's very small because you're using a very effective insulator. And then to get the interface temperature, so we're wanting to get the interface temperature here. No, ito yung steel mo, ito yung insulator, this is the outside and this is the inside. So this is 130, this is 25 degrees. You want to get the temperature here. So to get that, kukunin mo lang yung using the Q you've obtained, you equate it to the this being the outside and this being the inside. Okay, and then you can calculate 129 degrees Celsius, almost 130 degrees kasi halos tumagos lang lahat ng init dun sa steel, no? Meaning to say, kung wala yung insulation, sobrang laki ng heat na mawi-waste mo to the environment. So in heat transfer parlance, there is the thing which we call fouling, and it refers to the deposition of solid components onto the hot surface of the heat exchanger. So similar ito dun sa rice cooker ninyo na nagtututong, or let's say when you cook something, especially in a non-stick pan or yung mga maninipis na mga kaldero, at nagkakaroon ka ng mga burnt stuff there. Okay. So of course, this has a loss in terms of the food component kasi yung dumikit doon na nag-foul ay bahagi ng yield mo sana. Ikalawa, because these substances have much lower heat transfer coefficients than metal surfaces, then having a fouling layer build up on your heat exchanger could cause the heat transfer rate actual to go down, no? Kumbaga may thermal resistance siyang na-i-introduce sa inyong system. And particularly for, let's say, plate heat exchangers, this is a very, very big problem and it will affect your whole process kung hindi inagapan. So, bisitahin naman natin yung technicalities nitong fouling na ito ng mga technical foul at iba't ibang klaseng foul, okay? Singen-Heldman records 6 types of fouling. Precipitation, which happens when calcium salts cause scaling, and then chemical reactions that occur with your food materials, protein, sugars, and fats, particulate accumulation on the surface of the heat transfer surface, biofilm formation or attachment of micro and macroorganisms on the heat transfer surface. So pwede siyang maybe insect na namatay at dumikit doon or something. In terms of heat transfer cooling operations, so meron ding freezing. Kaya tayo merong scrape surface heat exchanger nga for that, di ba? And corrosion fouling when nag-react sa oxygen yung surface mo and if perhaps it's not properly passivated, then you might have corrosion. So take note that fouling could happen in both the inner and outer walls of your pipe. So definitely, depende kung ano yung gusto mong mangyari, maapektuhan yung heat transfer mo on both ends, no? If perhaps you want some more insulation dun sa labas ng pipe at nag-foul dun, then that might be a positive thing. Unless of course maybe nag-foul siya in such a way na nag-corrode, no? But anyway, ideally we would always have a clean pipe so it's easier for us to control our variable. Again, fouling may involve biofilm formation, which is the attachment of microorganisms forming a film that is not easy to remove, medyo malagkit and sticky, and then at the same time it protects the microorganisms from thermal treatment. So posibleng dahil meron silang resistance dahil sa biofilm na yan, ay hindi sila mamatay dun sa process schedule na alam mong supposedly mamapatay mo na sila. And then after they disperse, of course, they go back into your food and magpapaka-happy-happy sila doon. So let's now go on to the design of a tubular heat exchanger. Please take note that this is pretty basic and will not really cover the actual designing like from scratch, no? But basically the principles on how heat exchangers work. So when solving heat exchanger problems, in our case, we want to assume steady state conditions as previously defined, and that the heat transfer coefficient is constant over the pipe length, that such a uniform no yung material, and um, also that there is no axial conduction of heat in the metal pipe, no, puro radial, no, dun sa diameter pointing outwards instead of conducting along the pipe on either side. Next is that the heat exchanger is well insulated such that heat exchange happens only between the two fluids. In reality, that is not the case. However, to simplify the problems, you have to assume the negligibility of other heat exchanges unless otherwise mentioned. Also, that there is negligible heat loss to the surroundings. So, of course, these assumptions are ideal, but they do make our calculations easier. Heat exchangers are primarily designed to be either concurrent or countercurrent. In the case of concurrent, so H is for hot and C is for cold. Both the hot and cold fluids flow in the same direction. So if you would see in this graph, which is temperature profile versus the length of the pipe, or even residence time. So as you can see, the hot fluid and the cold fluid start hot and cold respectively at their inlet points. And as they progress through the pipes, or as time passes by, um, the delta T between the two of them becomes smaller. Okay, so the total heat transfer that happens is equal to the mass flow rate multiplied by the specific heat of, in this case, your product, and the temperature difference between the initial and final temperatures of the product. So we could do an energy balance on this based on our simplified assumptions. Okay, na lahat ng heat na galing sa hot fluid as its temperature goes down is absorbed by the cold fluid, and therefore you now have this simple energy balance equation over here. On the other hand, we also have the log mean temperature difference, or delta T Lm, which is the delta T they use in calculating the Q for the heat exchanger during heat exchanger design. No? So we'll see in the next slide kung alin yung delta T2 and delta T1, because this is dependent on whether concurrent or countercurrent yung heat exchanger flow mo. But basically, in heat exchanger design, you get the area of heat transfer and the log mean temperature difference, and multiply that by your U to get the your total Q. So the log mean temperature difference is calculated based on the difference between the left side and the right side of a heat exchanger. So inlet versus inlet, or inlet versus outlet, depending on the direction of the flow. By the way, this arrow should be pointing to the right, no? Magkamali dun sa book. Bakit ba natin nagkakaroon ng log mean temperature difference? Because it's safe to say yung delta T kasi between the hot and the cold fluid, hindi naman siya constant, di ba? So we want to get parang normalized temperature difference na to, yung pinaka-mean niya, but we cannot do that through algebraic means, kasi mukhang hindi naman algebraic yung relationship nito, or hindi naman linear lang, no? So that's why we use the LMTD. Okay. So if it's a concurrent heat exchanger, as is this case, again, yung arrow nitong nasa baba is pointing towards the right. Delta T1 would be the difference in temperature between the left-hand side. Okay, pati dito sa countercurrent heat exchanger. And the T2 would be yung right-hand side by convention. Usually by convention, we start with the highest temperature on the left side. Okay. So, please take note as well na yung countercurrent heat exchanger ay ganito po yung itsura niya. So, their temperature profile, since papasok yung hot fluid on the left side and the cold fluid on the right side, mas parang parallel curves yung dating ng profile nila, imbis na dito na gap na paliit ng paliit. So next we'll discuss surface characteristics and radiative heat transfer. When radiation hits an object, hindi naman ito lahat na-absorb, no? So we have the incident radiation, for example. Some of it gets reflected, some of it gets absorbed, some of it gets transmitted, and the object itself emits radiation, as we have seen. Now, this perhaps is not only seen in radiation, pero I mean, you can feel this siguro. Halimbawa, nagbukas kayo ng payong, may init na tatagos pa rin na mararamdaman mo. Depending on the material, alam mo na parang minsan nag-reflect ng init yung isang substance. And then at the same time, umiinit din yung payong mo, yung tela niya. Tapos may na-absorb siyang heat. So, kung ganun yung sa heat, ganun din yung sa radiation, of course, no? And each one of these things, yung absorption, reflection, and transmission, ay fractions na that when you add these absorptivity, reflectivity, and transmissivity values, they equal 1. So please take note that a black body absorbs all incident radiation, hence for a black body, absorptivity is 1 and the other two terms are 0. Also, a clarification, emissivity here is equal to absorptivity for the same wavelength. So the amount of light emitted is proportional to the absorptivity of your substance or material rather. So it's conventional now for us to choose, let's say, something white over something black, and we assume that the black colored thing, given that they're made of the same material, is absorbing more heat. So how true is this? For example, if you want to paint a rooftop and you want minimum heat gain from the sun during summer, can we actually sort of quantify that? No? So if we're comparing black paint and white paint, we have here the emissivity values for either shortwave or long wave radiation. So because sun has a very high temperature, solar radiation is classified as a shortwave, and therefore we will be using these values for the emissivity. And emissivity is equal to absorptivity, so we could equate these two to absorptivity. And if you were to assume zero transmittance, therefore the the reflectivity is equal to 1 minus the emissivity niya, no? So therefore we could see na mas marami kang mare-reflect na heat sa white paint versus black paint.